Thank you very much. Good morning, everybody. My name's Rob, and I'm going to be talking to you about what OpenFlow is and where it's going. So, a recent industry blog actually likened me to being the Kool-Aid man of OpenFlow. I'm not actually here to try to get you guys to drink the Kool-Aid. I mean, don't get me wrong, it's very good. You know, I made it myself. But unfortunately, for better or for worse, OpenFlow's got a lot of hype around it. And so really the purpose of this talk is for me to actually try to give you a good solid technical background as to what OpenFlow is and what it might be used for. So with that in mind, I'm going to be going through what are the backgrounds and problems that OpenFlow is trying to solve, what OpenFlow is itself, and the short answer there is OpenFlow is an API. If that's all you take from this talk, that's enough. Given this API, I'm going to give you some example use cases of why it might be useful to you in your network. I'm going to talk about the standardization efforts that are going on. It actually has a standards body, the Open Networking Foundation, specifically towards standardizing it. And there's already been some interoperability work going on. And last, I'm going to talk about the deployment and people who have started trying to adopt this thing. So before I get started into the talk, a little bit of a disclaimer. Most of this talk is about other people's ideas. OpenFlow is actually a fairly big movement, and I'm just the one speaking here today. There are a bunch of professors involved, a bunch of startups involved, all sorts of company, and even this new standards body. Specifically about me, I've been working on OpenFlow. I say in the trenches. I've been doing coding. I've been doing research. I've been working in the standards body for about 3 years now. I'm currently working for an OpenFlow-based startup, Big Switch Networks. But I'm really doing this talk with my OpenFlow evangelist hat on. This is not a company talk in any way. And kind of I guess with all the talks here, the opinions represented here don't necessarily represent those of the company. But so the big question is, what is the problem that OpenFlow solves? And if you talk to vendors here today or you talk to anybody, we have lots of solutions, right? What's a problem that we don't have a solution for? If you look across, the set of layers that we have, the sets of problems that we have, I mean, you can almost, Chinese menu style pick the solutions that you want. If you want virtualization in layer 2, you can use VLANs. If you want virtualization in layer 3, but MPLS, you've got VRF. If you kind of go through this chart and you imagine filling in all sorts of things, this is obviously very incomplete. There are all kinds of solutions here. What's the problem that we don't have? Well, the problem is that actually most people have a lot of these problems, and then you end up having to implement a lot of these solutions. And so what you really almost kind of want is a solution to the solutions. And so if you look at it another way, the argument is that complexity itself is the problem. So we've been having effectively a new solution for every problem for about 20 years now. And so our networks are actually very complex. And if you think about 20 years of what we've had right now in terms of complexity and different standards and different implementations, do you think we could handle another 20 more years of this? At what point do we get to a point where our networks can't actually be managed by humans who can only keep so many things in their heads at once? At what point is this a problem? And the kind of the insidious part of this is that the complexity feeds onto itself. It really compounds. That is to say, if you're managing multiple layers of your network and you have multiple things that you're interested in each one of these layers, you almost have this complex kind of Cartesian product of just complex solution spaces that you have to manage. Talking to this group about this, I feel like telling you that the sky is blue and the sea is the green. I mean, these things. And the bottom line is the complexity costs money. So it costs money in terms of taking longer to qualify new features and deploy them. And it costs longer in terms of trying to debug your network when there is a problem. And so, the big question is, okay, sure, the networks are complex. Yeah, I knew that. What can we do about it? And so I give you two kind of high-level answers. One is that we can find better abstractions. We can find ways of representing the network in slightly different, simplified ways. When we're making a config change, the individual config changes are less complex. We can stop solving the same problem in slightly different ways at different layers. And when we're solving a bunch of different problems, we can try to extract the commonality among the solutions. Another way that we can reduce complexity is to reduce the number of management touch points. That is, if you're going to make a config change, make it in fewer places. And this again is also kind of intuitive. I mean, people are already paying lots of money for these big multi-chassis systems, and there's a reason for it. It's much easier to manage one box that's logically a whole bunch of one logical box than a whole bunch of smaller boxes in its place. And we've seen this in other paradigms, the PCE and what have you, that really you're decoupling the control from the forwarding. You have fewer management touch points than you have forwarding nodes. So, sure, abstraction sounds like a neat idea, but what does this actually mean in practice? So if you kind of look inside a router, the names of these things change vendor by vendor, and depending on the model, these things change. But logically, you have something that does some sort of routing computation, and then you have a bunch of line cards. And so if you have a protocol, say BGP, that makes an announcement, so I can reach this network address on this interface. What happens is that message comes to a line card, and it gets punted up to the routing engine or whatever you want to call it. Some amount of computation happens. There's some routing recomputation that happens, and then a decision's made, and that decision is pushed down into the line cards in terms of the fib. And then so once this decision is in place, then packets can flow. So now when packets show up matching this IP prefix, we can actually make them go to the right direction. And so the critical thing is, this is actually the same process for MPLS if these were LDP messages. This is the same as OSPF, ISIS. And if you want to call the routing engine a supervisor module and say that this was actually a spanning tree message, it's even the same for switching. There's actually this very similar process going on for a lot of the protocols that we're talking about here. So there's a control message, there's some routing computation, and then there's a change to the forwarding entry. And so what is OpenFlow? OpenFlow is exactly an abstraction of this. So in terms of OpenFlow, OpenFlow is an abstraction and an API. And so the abstraction is we're going to take whatever we call the routing engine, the supervisor module, what have you, and we're going to call that an OpenFlow controller. And we're going to take the set of line cards, and we're going to call those the OpenFlow data path. And the data path is going to have inside it what I'm going to call a forwarding table. And I'll get into some of the details of what these things mean in a second. But critically, what we're going to do is we're actually going to standardize the communication path between these two things. So, and we're also going to put it over the network. And I'll come back, and so that's going to cause all sorts of concern for people, so just hold on to it for a second. Drink your coffee or bite your tongue or what you have. I'll explain this to you in a second. But so, these are definitely my older slides.
We can fix this.
All right. Is it possible there's a new file? That one, yeah. All right. Let me do that. Sorry for the interruption. These are still my older slides.
Oh, Mac is hard.
I see what's going on.
Yeah. I'm going to go up here.
There we
Sorry
go.
about that.
No.
There we go. All right.
Aha. So this is the picture we had, and this is the picture I wanted to show you. So what this means in practice is we're going to take the boxes that you have now, and you're going to get a new set of firmware from your router, your routing vendor. And they're going to put on that firmware an extra agent that runs on the box, and it's going to be an OpenFlow agent. And you're going to take a server somewhere in your network, and you can run a process on it that's going to be the OpenFlow controller. And then you're going to connect these things through a management network, and that protocol that they're going to speak is OpenFlow, and it's going to be over SSL. And so there's a whole bunch of things there. You're thinking, what vendor is going to support this? Do I really want to run Linux on a server? Do I want to develop this controller myself? All of these things are being worked out. So there are vendors that are going to supply OpenFlow controllers for you. In a lot of cases, the same people who are producing your routers are looking into developing OpenFlow controllers. And if you're worried about running things over your network, this is effectively what happens inside your box anyways. You can manage this connection just like you can manage any other connection in your network. But let me get back to that. So as I said, the controller is independent from this data path. It can run on an external server, it can run physically connected to the same box, it can run on a blade in the same box. The data path is your existing hardware plus new firmware, and that firmware does come from your existing router manufacturer. And the communication path over the network, we use TLS or SSL. It's something to do mutual authentication to make sure that we're actually talking to the right boxes. You can actually run this control network totally out of band in a physically dedicated management network. Or if that's not available to you, there are actually schemes to do this in-band inside in your actual control plane. But the critical thing I want you to take from this is this communication path between the control and the server is the open standard. That is what OpenFlow is. And so if you wanted to, and you were so inclined, and you happen to have an army of programmers, which actually some of you do, you could write your own controller. In fact, there's even a growing open source community for controller writers. That is, you could write your own routing algorithms. You could re-implement the existing routing algorithms. You could do what you wanted, which is actually really the crux of what OpenFlow is. Or if you don't have an army of programmers, there are lots of people who are interested in selling you OpenFlow controllers, if this solves problems that you have. So in terms of what the API actually does, it maps almost exactly to the diagram I showed you earlier with the router. You have the ability to punt packets up from the data plane to the controller. Imagine you running BGP and getting the control messages up to the control plane. You have the ability to do the reverse. You can source BGP control messages. You can source BGP hellos. And you have the ability to modify things that are in the forwarding path. And last, you have the ability to query statistics off of the boxes. So, getting interface counters or flow counters. So if you wanted to do, for example, dynamically reroute your network based on load. So these are all things that are available to you. Now, from an operator's perspective, this all seems very low level and probably crazy. You probably never want to actually programming an OpenFlow controller yourself. I mean, it depends who you are. But if you were a programmer, this is actually like giving the keys to the castle. Some of you were here, caught the Facebook Lightning talk, where they were saying that they want people to open up the box. This is actually everything that you would need out of the box to some approximation. And the idea is, what do you do with it? And so for some of you, the answer might just be you buy an OpenFlow controller and it solves problems for you, and this level of detail is never exposed to you. But for others, if you were open source inclined, or if you were actually happened to have an army of programmers, this is great. You now actually have control of exactly what's going on inside the boxes. So I mentioned there was this flow table. What does this actually mean? And so the flow table on the inside is really the core of deciding how the packet processing works. So the flow table has 3 elements. So a flow table entry has 3 elements. So it has a priority level, a set of match fields, and a action list. And really it's saying, if I see a packet that matches the following match forms, then apply this list of actions to it. And so you can think of this as a generalization of all switching and all routing all together. So matches are across any set of packet header fields. So you could say, if the packet is TCP and the destination is 22, then I want you to decrement the TTL and push it out a certain port. And then packets are matched in terms of the priority. So you can say, well, if it didn't match that, then check if the IP destination is to a certain prefix, and if that's true, then push it on to a certain quality service class queue. And if it didn't match any of those lower priority, then drop it. And so you can imagine that with the ability to program things at this level, and if you're familiar with how the hardware works, this is actually very much modeled after how TCAMs work or other types of CAMs. And all forwarding technology can, I shouldn't say all, but all the forwarding technology I'm aware of can be mapped onto something that looks like this. So this is really an abstraction of what is really on the deep underlying of the hardware. This is deep into the fib. And so you can almost think of OpenFlow as a fib programming API. But so once you have this, then you get back to this point of abstraction. So what can I do with this? And the answer is everything you can do now, you can actually do using these primitives and just express them in simpler ways. So what you think of switching today is really just matching on the layer 2 destination and forwarding out a port. What you think of as routing is matching on a layer 3 destination, decrementing a TTL, and forwarding out a port. Network access control becomes simply match the match pattern that you're interested, the ACL, and drop the packet. And then these are just the simple things. Now, the things that you can actually do lots of other things with this as well. So you imagine once you have a notion of multiple tables, which does exist in OpenFlow, you can even do more complex things. For example, VRF. So I'll match on an MPLS tag in a first table, and based on that, I'll go to a second table for a customer-specific forwarding prefix. And so in terms of OpenFlow standardization, people are constantly adding more fields to be matched on and more actions to be applied. And so that's really the crux of what OpenFlow is. So currently, you can match on layer 1 fields, what port did the packet come in on, layer 2 fields, the Ethernet destination, Ether type, Ethernet source, VLAN class of service, like the PCP bits. Layer 3, source destination IP, the protocol field. If it's IPv6, they're adding support for the flow identifier. Layer 4, you can match on the source destination ports. These types of things. In terms of actions, you get push, pop, and swap on VLAN and an MPLS. You can get rewrite actions. And all of these things are abstractions of what the hardware may or may not support. So the idea is we now have a mostly generic interface for programming most of the hardware out there. And there are online feature negotiations to say, okay, well, this specific box doesn't support this specific list of features. But in general, and there's actually a convergence in terms of what the ASICs are capable of, that it's actually fairly easy to map most of these things onto most of the hardware. And in fact, in a lot of cases, what's exposed to you as an operator is typically a subset of what the hardware is capable of. And so that's a very interesting aside about OpenFlow, is that quite often the thing that you want to do, the underlying hardware is capable of. It's just a matter of the network operating system may or may not have already exposed that. And so I mentioned there were two things that OpenFlow was trying to do. One was to do the abstraction, which I think I've covered a bit, and the other is to reduce the number of management touch points. And so we can do this because if you remember the picture that I drew, there's nothing that stops the OpenFlow controller from managing multiple data paths at the same time. So you can actually point multiple data paths at the same controller, reducing your number of management touch points. So the question that was probably on all of your minds right now is, how many do I do? How many controllers do I have? What happens if one of them dies? And I'll ask you not to panic. So there's nothing about OpenFlow that implies centralized control. You don't point all of your switches and routers at a single controller. The choice is up to you for what the relationship is between controllers and data paths. So if you are happy with how your networks work right now, you can actually get all of OpenFlow with one controller for each data path. Or maybe more likely, it makes sense actually to partition up your network in some way, and that some way ends up being a very deep network design question as a function of your requirements. But OpenFlow is totally orthogonal to how many controllers to switches you have, to data paths. And so you can imagine there's now a communication protocol between the controllers. Maybe something that looks like BGP, maybe that's something that's a hybrid of existing protocols, something that says, I know how to get to these boxes, oh, you know how to get to those boxes. And the other critical thing that the protocol has is a notion of failover. So when controller A dies, these boxes can fail over to controller B. And so these all might seem like fairly scary concepts, but they all have direct analogies into the boxes that you have today. If you have a multi-routing engine, multi-chassis box in your network, they actually are doing these things internal to the hardware. And typically there's an out-of-band, usually speaking Ethernet channel that connects your line cards up to these route engines. And they actually run a failover protocol that looks almost exactly like what's running here. So while this might sound crazy in concept, I claim this is actually very close to what you're already doing right now. And so this opens up lots of very interesting network design questions. So as I said, traditional networks run almost this one-to-one forwarding to control ratio of protocols. And so the big question is this the right thing for everyone? And if the answer is no, and I claim it's not, because if you look at things like BGP, so BGP is a one-size-fits-all protocol until the size doesn't fit you. And then people start using things like route reflectors and route aggregators, trying to make BGP fit better. And this is almost a generalization of that idea. So you get to these very interesting network design questions. How many controllers do I actually need? And it ends up being this a balance between how many management touch points am I willing to deal with versus what is the control traffic load that I have to manage? What is the failover rate that I want to recover from? So how many backup controllers do I need? Do I want a hierarchy of controllers even? And where do I put these controllers? Do I put a couple controllers per POP? Do I put them per geographic region? Do I put them per continent? And as I kind of alluded to, a lot of these are very similar questions that you would ask when deploying route reflectors or something similar. These are very network design, very specific to your network. And my claim is you can actually implement what exists today, and that's probably the right thing for some of you, but it's probably not the right thing for all of you. And one of the kind of benefits of OpenFlow is it lets you decide this ratio of forwarding paths to control paths as it fits for your network. I kind of flippantly said there's a protocol between controllers, and that's a big assertion. And by design, this is actually not part of OpenFlow. The idea is that this protocol between controllers is again going to be not one size fits all. It's going to be, and the idea is once you've actually pulled off the part that you need to standardize, the controller itself is just software. I mean, you can update that as fast as people update APIs to web search engines. If this is totally internal to your network, it doesn't need to be standardized. It'll probably help you in terms of the economics, but the idea is to decouple the intra control plane management from the OpenFlow standard, which is control plane to data plane. And so the benefit of this is it allows these things to evolve independently. You don't have to buy everything in one big silo. And you can, critically, we don't have to get, critically, one size does not fit all. And the solution that's going to help, another vendor is maybe not the right thing for you. Or another provider is not the right thing for you. And so what I want you to take from this picture is that OpenFlow is a building block towards a larger solution. It is not the entire solution. It is, you cannot run your entire network just using OpenFlow. You need more on top of it. But the claim is that this is a critical building block that we use to build up a larger, more complete solution. And the form of that solution will depend very much on your particular needs. That is, what are your failure requirements? What is do you have an external management network? How many forwarding nodes do you need to manage? How geographically dispersed are they? These are questions that, this is the essence of what network design is. And these are the things that you really don't want in a prepackaged, one-size-fits-all type format. So there are a lot of people working on kind of this bigger picture solution. And people are trying to define this as software-defined networking. So the way I look at software-defined networking is if you start with something that looks like OpenFlow on the bottom, there's kind of a layer, and then you would build on top of that, on top of some sort of API. And because there's this nice layer, you can actually decouple how it's implemented from what you want. And so imagine on top of this layer, you could build a load balancer, maybe a traffic engineering policy, delay estimator, and some sort of customer-facing API if you wanted to follow Dave Ward's example from yesterday. But so the thing I want you to take from this is all independent from OpenFlow by design. What you do with OpenFlow is totally different from how it works and why you might want it. And so just to put things in perspective, what's under this line is what I'm talking about in this talk. And for example, and he's not the only one, above this line is what Dave was talking about yesterday. And so the critical difference here is what's above the line, in my mind, is too early to standardize, if at all. I mean, this is really your customer, this is your business logic. This is what you want to do with your network. And this is something that should be highly prized by your company and maybe not standardized and pushed through to a larger audience. There are a lot of very smart people in this room that have heard of all sorts of protocols that have come and gone in my time, and I'm sure there are a large fraction of you sitting there thinking, OpenFlow is just the same as blah, blah, blah. And I can't actually sit here and go through all possible instances of blah, blah, blah to convince you that it's actually different. Popular things that I've heard are OpenFlow is the same as Lisp, OpenFlow is the same as MPLS-TE, as policy-based routing. I heard soft circuits yesterday. The kind of broad answer, since I don't really have, the answer is different by protocol, but the broad answer is that OpenFlow is this very low-level API. It's almost a thin wrapper around what the ASICs are actually capable of. And so, yes, you probably could implement blah, blah, blah with OpenFlow, but conversely, you probably couldn't implement OpenFlow with blah, blah, blah. So OpenFlow is, in that way, almost a superset of these protocols. And the other question is, if I already have blah, 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 why would I need OpenFlow? The obvious answer is, if you're happy with your networks as they exist today, this is not a technology for you. But my guess is that most of you could deal with the networks being a little bit less complex. It might make your lives a little easier, and you might sleep a little better at night. And the claim is that if you were using OpenFlow, and this is obviously a grandiose claim with a bit of hand waving, and maybe there's some Kool-Aid splash on the side, but the claim is that using OpenFlow can give you a more holistic view of your network, and you can reduce the complexity from the feature and the layer interaction. And so for any specific instance of blah, 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 there's probably not a win. And if you only run this one protocol on your network, maybe OpenFlow is not the right thing for you. But if you're running lots and lots of protocols at lots of layers across your network, this is something to consider. This is actually, I said a strong technical foundation, and I hope I met at least some of that, but there's obviously a lot more to OpenFlow. So some pointers, there's openflow.org, there's actually the full public specification there, a whole lot of online tutorials. Stanford has its own site with lots of open source things. There's a OpenFlow-based hypervisor, which I wrote, a bunch of OpenFlow controllers that are free for you to download and build on. If you aren't interested in applying OpenFlow firmware to things that are in your network right now, there's actually an OpenFlow network emulator that you can use just to try out and play around with called Mininet. And there's actually a pretty large growing base of people and tools being developed in this space. And these URLs are at least the places to get started. So that's what OpenFlow is. Let me see if I can cover some use cases to convince you guys this might be interesting in your particular networks. So at a high level, OpenFlow is an API that enables lots and lots of different use cases. In my mind, the sky is the limit for what you could actually do with it. But really to spark your imagination for this talk, I've cherry-picked a couple set of use cases that I think are be interesting to this group. And I picked them kind of with a service provider emphasis. All the use cases I'm going to cover have been demonstrated at Stanford in wide area networks. So we know they work at some level. And it's worth mentioning that I think almost to every point, while the demonstrations I'm showing are very slapdash proof of concepts run by grad students, my claim is that I think that all of them have commercial companies that are working on production grade solutions for you if you're interested. And if you don't see the use case that you like here, there's actually a lot more complete with videos online at the link here off the OpenFlow website. But so, one of the biggest interesting use cases with OpenFlow is actually virtualization. So there's two cases where I think virtualization is really of interest to service providers. One is if you're running something like a virtual tenant network and your clients, your tenants, actually want more direct control over their network. So maybe they want to create a VLAN within their virtual tenant network, or maybe they want to do access control lists within their virtual tenant network. And so my understanding in practice today, what that turns out to be is they call you, and then you open the config file, you think a little bit, and you say, well, I guess this won't break everything, and then you edit the config file and you apply this. And this is actually not terribly scalable. And so the idea is, and this is actually the tool that I've developed, you could actually, as the operator of the network, run an OpenFlow controller, which is effectively a hypervisor. Something that says, I'm going to give Alice, customer Alice, control of any traffic that happens to match her MPLS tag, or anything that matches her IP prefix. And she can do anything she wants with traffic that matches this list of rules. And then I'm also going to ensure that she can't affect any traffic that doesn't match this list of rules. And so you can now let Alice create ACLs, she can create MPLS tags or do what she wants, as long as it matches the rules that you set aside for her. And you can set aside different rules for different customers. And there's actually logic to make sure that the rules are overlapping and sane in some way. And if, for example, you had a customer interested in OpenFlow itself, that this is another thing. You can actually re-expose OpenFlow directly to them with the understanding that they can only impact the traffic that you've given them access to. And so maybe you're not a virtual tenant network. Maybe you're a large over-the-top provider, but you happen to run a bunch of services. Maybe you have a mail service. Maybe you have a video streaming service. This ends up being interesting to you as well because you could think of these different groups as different customers. And maybe you can give the video streaming people the ability to load balance their traffic in a way that they want without impacting without having to make the mail folks go through the same load balancer. Something else that's interesting to people is, I guess Dave Ward called it cloud bursting. This is a subset of this. I think of this just as wide area WAN migration. So the idea is you've got a wide area VM migrations. The idea is you have a VM. It has active connections to it. You want to move it from one data center to another while keeping the same IP without having to alert the clients or change the protocols or anything like that. So the idea is with OpenFlow, what this looks like is you talk to the OpenFlow controller, you say, I'm moving the VM from A to B, update all of the forwarding tables along the path, and just transparently, without the source or the destination knowing it, reroute the path. And so this looks a lot like IP Anycast, except the control channel is out of band. And so the demo that we did actually at Stanford was the sources here were actually clients to a first-person shooter game. And the server was actually a first-person shooter server, and we had clients playing the game as we migrated the VM from California to Japan, while maintaining the same IP address without interruption of service. I'm actually going to skip this in the interest of time. Another use case is actually reducing energy efficiency, energy costs in data centers. So most data centers are built out for peak usage, which means during non-peak times, there's a substantial fraction of your network that's not doing anything, and fraction of hosts. So the idea is if you had this OpenFlow level control of routing, you could actually power down unused fractions of your network and intelligently route around them. And so this very simple idea, depending on your connectivity and your usage patterns, can actually save a fair bit of electricity. And for a lot of you, that ends up being a fairly dominant cost. For each of these, by the way, if you're interested in them, there's in-depth videos and even papers off of the OpenFlow website. So if there's something here that I'm not covering the level of detail that's sufficient for you guys, that's definitely the place to start. Or just grab me in the hallway, of course. In terms of standardization, there's this newly formed Open Networking Foundation. It's now charged with maintaining all of OpenFlow and its related protocols. OpenFlow originally came out of Stanford University, and there was some initial attempts, haphazard to do standardizations body out of Stanford, and those didn't work very well. The Open Networking Foundation is composed of promoters and adopters, and I'll get to what that means. But critically, if you're a promoter or adopter, you agree to cross-license all of the IPR to all of the other members royalty-free. So the question that you're all asking yourselves is, why is this not in the IETF? And you should ask Dan Pitt, the creator of the Open Networking Foundation. But my belief is the answer is the IPR policy. There was concern that a great way to kill something like OpenFlow would be to put something copyrighted into the standard and then kill it. And so the notion of the Open Networking Foundation is explicit to avoid that. In terms of its board, these are the promoters. There's actually a pretty substantial list of large operators that have joined this. And I think actually all of them are represented here today. So that's a good step. In terms of the adopters, there's almost every vendor that you can think of has at least decided to join the Open Networking Foundation, participate in the standardization, at least find out what's going on. I'll give you guys a second here to read this slide, just to make sure that either your company is on this list or your providers are. We also ran a pretty sizable Interop fest at Interop. Critically, after a fair bit of work and duct tape and baling wire, we're actually able to get OpenFlow implementations from 14 different vendors to interoperate under a single controller. So on the right, we have a list of all the vendors who have participated. This does not mean that these vendors have commercial products that you can buy from them. But if you see vendors on this list that you work with and you are interested in OpenFlow, all of these vendors are deciding what to do with OpenFlow at this point, so your input is probably appreciated by them. I'm very quickly to go through what deployments exist. There's a big caveat that these are all the public deployments that people can talk about. There are even larger private deployments where the details are non-public and scarce. If you're interested in finding out about those, your best bet is to find a member operator that's at the convention here and buy them a beer. We know of over 70 deployments worldwide. Most of these are a couple guys in a lab have downloaded an OpenFlow switch and are using it for their internal traffic. Slightly larger, there's a National Science Foundation project called Genie. This has expanded this out to a bunch of different campuses. If you're familiar with Internet 2, it's another research and education network. They have planned to go out to 34 POPs of OpenFlow spread across the country. And they're similar to the NSF Genie project. There's the Ophelia project in Europe, spread across 5 countries there. And so these are all OpenFlow-based networks available for people to use. So kind of jump through the last bit there very quickly, running a little out of time, but I want to allow some time for questions. But the high-level point is, my claim is that networking needs better abstractions in order to reduce complexity. OpenFlow is an abstraction and an API. And time will tell if it is the right abstraction, but my claim is that it's at least asking the right questions, and we'll see what the results are. There are lots of use cases that might be of interest to you. I've only hit on a couple of them here. And OpenFlow is on its way towards widespread adoption in terms of the ONF and the number of deployments. So thank you very much for your time, and I'll take questions.
So we have just a couple minutes for questions. We'll start on the left.
Good morning. Jeff Sachs from Blue Ridge Internetworks. So you said a couple of times in the middle of the talk that what you were showing was perhaps scary. And I wasn't scared by most of it because I agree with you. That's about what's happening inside most large chassis-based switches. But the scariest thing to me is what happens when packets need to be punted to the controller. Does that mean that every time some workstation needs to ARP for the gateway, that an ARP packet has to be encapsulated in SSL and sent across the continent?
So the way that it works in practice is that the controller decides what gets punted to the controller. So the rule is anything that does not match in the forwarding table gets punted up. And so if you don't want ARP to get punted up to the controller, you can insert a forwarding rule that matches ARP that says, here is the places I want you to send it. So you can imagine putting together something that looks like a STP tree or something like that to manage that. But at the same time, there are applications where you might want to punt ARP up to the controller. For example, if you were trying to do managed ARP, and maybe you provisioned your controllers so that they weren't on the other side of the country, there was one per pop or something like that. I mean, so the critical thing to take away from this is that OpenFlow lets you pick either of those solutions, and either of those two solutions will be right for some people and wrong for the others.
All right, so we'll close the mics here. Those people in line can ask their questions, and then we'll move on. Center microphone.
I have 3 comments. With respect to ARP, I think it has to be done locally or you won't be able to talk to the network controller. It makes no sense to punt it to a controller. That's something that's probably local to the box, so you probably want it there. You made a comment about the OpenFlow controller is just like the route engine, but it's externalized. Well, not really, because you can't get rid of the route engine, so there's some things that have to still stay there, and you have to decide which is going to stay there and which is going to be put remotely. So that's kind of a design decision that's going to be critical to be made. With respect to punting packets, today router vendors struggle quite a bit with the round trip time between punting a packet to the routing engine and then programming all the line cards and keeping the fib synchronized. We always try to optimize that so the non-synchronization time is kept to less than milliseconds, and it's really a big challenge. So the RTT time now, when you have to punt all the way to a network controller and back, are going to be orders of magnitude. So you have to decide what you punt. You have to be very judicious on what gets punted.
Are these comments or questions? Because I can give
comments.
answers.
Oh, you want to respond? Please go ahead.
So I mean, exactly as I was saying. I mean, if you think about, inside a multi-router chassis, off a line card, they have something that looks like a host that actually will do ARP to figure out where the route engine is, and there's effectively a different management control network that manages those connections, right? And very similar with OpenFlow, from the route engine.
But you're still going to need ARP, right?
You still need ARP. But the idea is it's a different network. You can almost think of these things as internally as routers.
Doesn't matter, because the ARP and the network controller will add no value if they have to keep it locally. I mean, most vendors will make the decision.
It's different ARPs. So if I'm ARPing across my data plane, it's very different from an ARP across my control plane.
You ARP for both reasons.
It's true, but if Alice is trying to get to Bob, that generates an ARP message, which is very different from the ARP message that's generated from the controller. If we want to talk about this over whiteboard, it might be easier.
If you program the fib from the network controller and you don't have the next hop MAC address, you got to get it. So is the network controller going to provide all the information, or do you split the functionality? If you're doing it for controller data,
I mean, this is the earlier question. There are right answers, and these things depend on your network.
Yeah. Okay. And
Sir, thanks.
Oh, there's one more.
No, we have other people in line. I'm sorry.
Feel free to grab me offline, and we can continue to discuss this.
Hi, Patrick Gilmer from Akamai Technologies. You mentioned that, for instance, the hardware supports many more things that are exposed in the UI. The router vendors, for good or for bad, actually frequently hide things because it causes performance problems, for instance, on this. What is there, or do you have some way to make sure that the OpenFlow controller is not asking the hardware to do something that will decimate whatever else is going on in the box?
Two quick answers to that. There are some level of capability negotiations in the OpenFlow protocol. So the controller can say, hardware, can you do this? The other answer to that is, much like on the routing engine, the OpenFlow controller assumes some level of competence in the programmer. So
well, that was a mistake.
Well, yes and no. I mean, it's the competence. You make that assumption, or you cost in performance. And so in some ways, the OpenFlow is a loaded gun pointed at your foot. It's up to you to decide how to use it.
Fair point. Thank you very much. Very good presentation. Thanks.
Thank you.
Who are you? Where are you from?
Dan McGrayan, Johns Hopkins APL. Okay, so you can see why this tool is much beloved by researchers, obviously. I don't think you've really made the case yet to this community of why operators, should turn themselves into programmers. I think there are, a subset of corner cases where people who are really seriously into DIY, like the Facebooks or whatever, who basically want to, strip the intelligence out of 10,000 switches, basically write their own protocols and slam stuff into that. That's clearly the case. I could see those kind of cases. But, the idea, when you make the complexity argument and you're saying, okay, there are all these different matrices of protocols, that's because a lot of people do things in a lot of different ways, not one size fits all, right? So I think that, it's, as soon as you start saying, okay, in DIY you can simplify everything yourself, you can do it all your own way. But I think the idea that somehow people are going to reinvent BGP on their own is, absurd, really. But if you want to do it yourself and everybody does it all in different ways, you're going to just reinvent all that kind of matrix of complexity, right? So, you can always go back to first principles and kind of do everything yourself by getting down to basics, kind of like programming and machine language, right? But most of the time, what people want is they want to pay their vendor to implement that protocol for them, and that's why you have all the costs, 3/4 of the costs by router vendors is in their software development. Which, by the way, software-defined networking, I think it really should be called DIY software-defined networking. That's part of the hype. Okay.
So if I may.
Sure.
So if I gave too much of a DIY spin on this, that's my own personal bias, and I apologize for that. I tried to throw in there as much as possible that, and I think I might even have said this explicitly, that for a lot of you, OpenFlow itself is not interesting. It's the solutions that it enables. There are sets of solutions that are possible only because it's simpler for someone else to implement. If you think about the virtualization example that I gave, that's going to be very hard for someone to implement. Say Cisco, say Juniper tries to implement this using existing configuration files. You really need an internal restructuring for that to happen. And for that, maybe use OpenFlow, maybe you don't. And from an operator perspective, this is irrelevant. These are implementation details, and I certainly can see that point. At the same time, without a community push towards something like this, the operators do not have the right financial incentives to do things, to revamp the solutions. They're making lots of money. And these are my personal opinions. I apologize if I'm offending anyone here, but there is not a financial incentive for them to rewrite the protocols. Not rewrite the protocols, but re-implement the protocols using something that's ultimately simpler. And so, while this might have been my fault because it's my own personal bias, I've pitched this almost from a programmer's standpoint. There really are benefits to be had to non-programmer operators in this.
Yeah, well, we'll see.
We'll see, exactly. Thank you for the question.
Rob, thank you. We got to cut it off here because we're over time, but thank you for your presentation.
Thank you very much.